Okay, let's continue with the paragraph 2.1.3, what is meant by data. So we began the rational number implementation in section 2.1.1 by implementing the rational number operations add ret, subret, and so on in terms of three unspecified procedures: make ret, numer, and denom. At that point, we could think of the operations as being defined in terms of data objects, numerators, denominators, and rational numbers, whose behavior was specified by the latter three procedures. But exactly what is meant by data? It is not enough to say whatever is implemented by the given selectors and constructors. Clearly, not every arbitrary set of three procedures can serve as an appropriate basis for the rational number implementation. We need to guarantee that if we construct a rational number x from a pair of integers n and d, then extracting the number and the denom of x and dividing them should yield the same result as dividing n by d. In other words, make ret, numer, and denom must satisfy the condition that for any integer n and any non-zero integer d, if x is make ret of n and d, then the numer of x divided by the denom of x is equal to n divided by d. In fact, this is the only condition make ret, numer, and denom must fulfill in order to form a suitable basis for a rational number representation. In general, we can think of data as defined by some collection of selectors and constructors, together with specified conditions that these procedures must fulfill in order to be a valid representation. This point of view can serve to define not only high-level data objects, such as rational numbers, but lower-level objects as well. Consider the notion of a pair, which we used in order to define our rational numbers. We never actually said what a pair was, only that the language supplied procedures cons, char, and coulter for operating on pairs. But the only thing we need to know about these three operations is that if we glue two objects together using cons, we can retrieve the objects using char and coulter. That is, the operations satisfy the condition that for any objects x and y, if z is cons of x and y, then char z is x and coulter z is y. Indeed, we mention that these three procedures are included as primitives in our language. However, any triple of procedures that satisfies the above condition can be used as the basis for implementing pairs. This point is illustrated strikingly by the fact that we could implement cons, char, and coulter without using any data structures at all, but only using procedures. Here are the definitions. Mm. So basically here we are defining the procedure cons, and inside that we are defining another procedure, dispatch, that takes an argument m and if that argument is 0, it returns x. If m is equal to 1, it returns y, and otherwise returns an error. And then we define car of z as z0. There is something odd with this definition. I don't understand what that dispatch is. This one. This doesn't make sense. Car Z in the procedure is Z 0. Maybe I'll continue to read and everything will be clear. This use of procedures corresponds to nothing like our intuitive notion of what data should be. Nevertheless, all we need to do to show that this is a valid way to represent pairs is to verify that these procedures satisfy the condition given above. The subtle point to notice is that the value returned by cons xy is a procedure. Okay. Namely, the internally defined procedure dispatch, which takes one argument and returns either x or y, depending on whether the argument is 0 or 1. Correspondingly, car z is defined to apply z to 0. Yes, but z, where did I define z here? Here z is not defined. I was expecting define z as the cons xy. Hence, if z is the procedure formed by cons xy, then z applied to 0 will yield x. Okay, now I agree and I see, but here the definition of z is missing. Okay, these are all only the definitions of cons, car, and z, of cons, car, and Cuder. I see, I see. Okay. Okay. Thus, we have shown that car of cons xy yields x as desired, and similarly, Cuder applies the procedure returned by cons xy to 1, which returns y. Therefore, this procedural implementation of pairs is a valid implementation. And if we access pairs using only cons, car, and Cuder, we cannot distinguish this implementation from one that uses real data structures. The point of exhibiting the procedural representation of pairs is not that our language works this way, Scheme and Lisp systems in general implement pairs directly for efficiency reasons, but that it could work this way. The procedural representation, although obscure, is a perfectly adequate way to represent pairs, since it fulfills the only conditions that pairs need to fulfill. This example also demonstrates that the ability to manipulate procedures as objects automatically provides the ability to represent compound data. This may seem a curiosity now, but procedural representations of data will play a central role in our programming repertoire. This style of programming is often called message passing, and we will be using it as a basic tool in Chapter 3 when we address the issues of modeling and simulation. And here we have the exercise 2.4. Let me see if it can be interesting. Alternative representation using lambda. Okay. Okay, I will take a look. I will take a look. Okay, other exercises. An extended exercise. Interval arithmetic. Not sure if I want to go through this. No. I don't think so. Other exercises, a lot of exercises. Maybe I will do a couple of those. Lot of exercises. Hierarchical data and the closure property. As we have seen, pairs provide a primitive glue that we can use to construct compound data objects. Figure 2.2 shows a standard way to visualize a pair. In this case, the pair formed by cons 1 and 2. In this representation, which is called box and pointer notation, each object is shown as a pointer to a box. The box for a primitive object contains a representation of the object. For example, the box for a number contains a numeral. The box for a pair is actually a double box, the left part containing a pointer to the car of the pair and the right part containing the coder. We have already seen that cons can be used to combine not only numbers but pairs as well, as we did in exercise 2.2 and 2.3. As a consequence, pairs provide a universal building block from which we can construct all sorts of data structure. Figure 2.3 shows two ways to use pairs to combine the numbers 1, 2, 3, and 4. Okay, I see. Box and pointer. Okay, the ability to create pairs whose elements are pairs is the essence of list structure's importance as a representational tool. We refer to this ability as the closure property of cons. In general, an operation for combining data objects satisfies the closure property if the result of combining things with that operation can themselves be combined using the same operation. Closure is the key to power in any means of combination because it permits us to create hierarchical structures structures made up of parts which themselves are made up of parts, and so on. From the outset of Chapter 1, we have made essential use of closure in dealing with procedures, because all but the very simplest programs rely on the fact that the elements of a combination can themselves be combinations. In this section, we take up the consequences of closure for compound data. We describe some conventional techniques for using pairs to represent sequences and trees, and we exhibit a graphics language that illustrates closure in a vivid way. Okay? Representing sequences. One of the useful structures we can build with pairs is a sequence, an ordered collection of data objects. There are, of course, many ways to represent sequences in terms of pairs. One particularly straightforward representation is illustrated in figure 2.4, where the sequence 1, 2, 3, 4 is represented as a chain of pairs. Okay, basically, in every pair you have the number and then a pointer to the subsequent to the subsequent pair that contains the number, and the pointer to the next pair, and so on. Until basically in the last element of the chain you have a null pointer that is pointing nowhere. The car of each pair is the corresponding item in the chain, and the coder of the pair is the next pair in the chain. The coder of the final pair signals the end of the sequence by pointing to a distinguished value that is not a pair, represented in box and pointer diagrams as a diagonal line, and in programs as the value of the variable nil. Yes, that's null pointer. The entire sequence is constructed by nested cons operations. Such a sequence of pairs formed by nested conses is called a list, and Scheme provides a primitive called list to help in constructing lists. The above sequence could be produced by list 1, 2, 3, 4. And in general, I guess that here A1, A2, and AN can be any data. So these could be numerals, but also can be pairs or other data structures. Lisp systems conventionally print lists by printing the sequence of elements enclosed in parentheses. Thus, the data object in figure 2.4 is printed as 1, 2, 3, 4. Okay, we have an example. Be careful not to confuse the expression list 1, 2, 3, 4 with the list 1, 2, 3, 4, which is the result obtained when the expression is evaluated. Attempting to evaluate the expression 1, 2, 3, 4 will signal an error when the interpreter tries to apply the procedure 1 to arguments 2, 3, and 4. Yes. We can think of car as selecting the first item in the list, and of coder as selecting the sublist consisting of all but the first item. Nested applications of car and coder can be used to extract the second, third, and subsequent items in the list. The constructor cons makes a list like the original one, but with an additional item at the beginning. Okay. Okay. The value of nil used to terminate the chains of pairs can be thought of as a sequence of no elements, the empty list. The word nil is a contraction of the Latin word nihil, which means nothing. The use of list operations, the use of pairs to represent sequences of elements as lists, is accompanied by conventional programming techniques for manipulating lists by successively codering down the lists. For example, the procedure list_ref takes as arguments a list and a number n and returns the nth item of the list. It is customary to number the elements of the list beginning with 0. The method for computing list_ref is the following. For n equal to 0, list_ref should return the car of the list. Otherwise, list_ref should return the n-1st item of the CUDR of the list. Should return the n-1 item of the CUDR of. Okay, yes. I see. Yeah, here we have the definition. Often we CUDR down the whole list. To aid in this, scheme includes a primitive predicate null, which tests whether its argument is the empty list. The procedure length, which returns the number of items in a list, illustrates this typical pattern of use. Okay. Okay, the len procedure implements a simple recursive plan. The reduction step is the length of any list is 1 plus the length of the CUDR of the list. This is applied successively until we reach the base case. The length of the empty list is 0. We could also compute length in an iterative style. Yes, of course. Another conventional programming technique is to cons up an answer list while CUDRing down a list, as in the procedure append, which takes two lists as arguments and combines their elements to make a new list. Append is also implemented using a recursive plan. To append lists, list 1 and list 2, do the following. If list 1 is the empty list, then the result is just list 2. Otherwise, append the CUDR of list 1 and list 2 and const the car of list 1 onto the result. Okay. And we have a bunch of exercises. Okay. Maybe I'll do a couple of these. Mapping over lists. One extremely useful operation is to apply some transformation to each element in a list and generate the list of results. For instance, the following procedures scales each number in a list by a given factor. Okay. I guess there is already a procedure that allows to apply a function and apply a procedure over a list. We can abstract this general idea and capture it as a common pattern expressed a higher order procedure, just as in section 1.3. The higher order procedure here is called map. Indeed. Map takes as arguments a procedure of one argument and a list, and returns a list of the results produced by applying the procedure to each element in the list. Okay, nothing new. This is quite standard. Okay, in this case, for example, we are applying the absolute value function to each element of this list, and we can also use an inline procedure using the lambda. Map is an important construct, not only because it captures a common pattern, but because it establishes a higher level of abstraction in dealing with lists. In the original definition of scale lists, the recursive structure of the program draws attention to the element by element processing of the list. Defining scale list in terms of map suppresses that level of detail and emphasizes that scaling transforms a list of elements to a list of results. The difference between the two definitions is not that the computer is performing a different process, because it isn't, but that we think about the process differently. In effect, map helps establish an abstraction barrier that isolates the implementation of procedures that transform lists from the details of how the elements of the list are extracted and combined. Like the barriers shown in figure 2.1, this abstraction gives us the flexibility to change the low-level details of how sequences are implemented, while preserving the conceptual framework of operations that transform sequences to sequences. Section 2.2.3 expands on this use of sequences as a framework for organizing programs. And another exercise. Okay, a lot of exercises in this chapter. Yeah, let me see. Always show sidebar. We are here. Hierarchical structures. Okay. Let's finish this section. I want to conclude the recording at symbolic data. Remove the sidebar. Okay. Hierarchical structures. The representation of sequences in terms of lists generalizes naturally to represent sequences whose elements may themselves be sequences. For example, we can regard the object list that contains a list and two other numerals. So a list of 3 items, the first of which is itself a list. Indeed, this is suggested by the form in which the result is printed by the interpreter. Figure 2.5 shows the representation of this structure in terms of pairs. Another way to think of sequences whose elements are sequences is as trees. The elements of the sequence are the branches of a tree, and the elements that are themselves sequences are subtrees. Figure 2.6 shows the structure in figure 2.5 viewed as a tree. Recursion is a natural tool for dealing with tree structures, since we can often reduce operations on trees to operations on their branches, which reduce in turn to operations on the branches of the branches, and so on, until we reach the leaves of the tree. As an example, compare the... let's see. Okay, this is the tree representation of the list discussed above. Sorry. As an example, compare the length procedure with the count leaves procedure, which returns the total number of leaves of a tree. Count leaves. sorry, where we procedure. Okay, to implement count leaves, recall the recursive plan for computing length. Length of a list x is 1 plus length of the coulter of x. The length of the empty list is 0. Count leaves is similar. The value for the empty list is the same. Count leaves of the empty list is 0. But in the reduction step, where we strip off the car of the list, we must take into account that the car may itself be a tree whose leaves we need to count. Thus, the appropriate reduction step is count leaves of a tree x is count leaves of the car of x plus count leaves of the coulter of x. So let me think about it. So this is a breadth first algorithm, because basically each time you are don't know, you have to think about it. Finally, by taking cars we reach actual leaves, so we need another base case. Count leaves of the leaf is 1. To aid in writing recursive procedures on trees, Scheme provides the primitive predicate pair, which tests whether its argument is a pair. Here is the complete procedure. Okay, not pair, basically you are in a leaf, and otherwise you use recursion to visit all the subtrees. Okay. Exercises. Lot of exercise. Mapping over trees. Just as map is a powerful abstraction for dealing with sequences, map together with recursion is a powerful abstraction for dealing with trees. For instance, the scale tree procedure, analogous to scale list of section 2.2.1, takes as arguments a numeric factor and a tree whose leaves are numbers. It returns a tree of the same shape where each number is multiplied by the factor. The recursive plan for scale tree is similar to the one for count leaves. Okay, basically you are navigating the tree with this condition until you find the leaf and you multiply that numeral by a factor. Okay. Another way to implement scale tree is to regard the tree as a sequence of subtrees and use map. We map over the sequence, scaling each subtree in turn, and return the list of results. In the base case, where the tree is a leaf, we simply multiply by the factor. Okay. Many tree operations can be implemented by similar combinations of sequence operations and recursion. Okay, more exercises, a lot of exercises. Sequences as conventional interfaces. In working with compound data, we've stressed how data abstraction permits us to design programs without becoming enmeshed in the details of data representations, and how abstraction preserves for us the flexibility to experiment with alternative representations. In this section, we introduce another powerful design principle for working with data structures, the use of conventional interfaces. In section 1.3, we saw how program abstractions implemented as higher order procedures can capture common patterns in programs that deal with numerical data. Our ability to formulate analogous operations for working with compound data depends crucially on the style in which we manipulate our data structures. Consider, for example, the following procedure, analogous to the count leaves procedure of section 2.2.2, which takes a tree as argument and computes the sum of the squares of the leaves that are odd. On the surface, this procedure is very different from the following one, which constructs a list of all the even Fibonacci numbers until k, where k is less than or equal to a given integer n. Despite the fact that these two procedures are structurally very different, a more abstract description of the two computations reveals a great deal of similarity. The first program enumerates the leaves of a tree, filters them, selecting the odd ones, squares each of the selected ones, accumulates the results using plus starting with 0, and the second program enumerates the integers from 0 to n, computes the Fibonacci number for each integer, filters them selecting the even ones, and accumulates the result using cons starting with the empty list. So there is the signal flow plans for the procedure that we are talking about reveal the commonality between the two programs. Basically, we have this enumerate, filter, map, accumulate, enumerate, map, filter, and accumulate. A signal processing engineer would find it natural to conceptualize these processes in terms of signals flowing through a cascade of stages, each of which implements part of the program plan, as shown in figure 2.7. We begin with an enumerator, then we have a filter, then we have a map, then we have an accumulator. Unfortunately, the two procedure definitions above fail to exhibit this signal flow structure. For instance, if we examine the sum odd squares procedure, we find that the enumeration is implemented partly by the null and pair tests and partly by the tree recursive structure of the procedure. Similarly, the accumulation is found partly in the tests and partly in the addition used in the recursion. In general, there are no distinct parts of either procedure that correspond to the elements in the signal flow description. Our two procedures decompose the computations in a different way, spreading the enumeration over the program and mingling it with the map, the filter, and the accumulation. If we could organize our programs to make the signal flow structure manifest in the procedures we write, this would increase the conceptual clarity of the resulting code. Sequence operations. The key to organizing programs so as to more clearly reflect the signal flow structure is to concentrate on the signals that flow from one stage in the process to the next. If we represent these signals as lists, then we can use list operations to implement the processing at each of the stages. For instance, we can implement the mapping stages of the signal flow diagrams using the map procedure. Filtering a sequence to select only those elements that satisfy a given predicate is accomplished by Okay, here we are defining a filter, we are defining accumulation. All that remains to implement signal flow diagrams is to enumerate the sequence of elements to be processed. For even fibs, we need to generate the sequence of integers in a given range, which we can do as follows. Okay. To enumerate the leaves of a tree, we can use enumerate tree, blah blah blah. Now we can reformulate some odd squares and even fibs as in the signal flow diagrams. Yes, now we have accumulate, map, filter, and enumerate. In the same for the Fibonacci sequence. The value of expressing programs as sequence operations is that this helps us make program designs that are modular, that is, designs that are constructed by combining relatively independent pieces. We can encourage modular design by providing a library of standard components together with a conventional interface for connecting the components in flexible ways. Modular construction is a powerful strategy for controlling complexity in engineering design. In real signal processing applications, for example, designers regularly build systems by cascading elements selected from standardized families of filters and transducers. Similarly, sequence operations provide a library of standard program elements that we can mix and match. For instance, we can reuse pieces from the sum of squares and even fibs procedures in a program that constructs a list of the squares of the first n plus 1 Fibonacci numbers. We can rearrange the pieces and use them in computing the product of the squares of the odd integers in a sequence. We can also formulate conventional data processing applications in terms of sequence operations. Suppose we have a sequence of personnel records and we want to find the salary of the highest paid programmer. Assume that we have a selector salary that returns the salary of a record, and a predicate programmer that tests if a record is for a programmer. Then we can write this. These examples give just a hint of the vast range of operations that can be expressed as sequence operations. Sequences implemented here as lists serve as a conventional interface that permits us to combine processing modules. Additionally, when we uniformly represent structures as sequences, we have localized the data structure dependencies in our programs to a small number of sequence operations. By changing these, we can experiment with alternative representations of sequences while leaving the overall design of our programs intact. We will exploit this capability in section 3.5 when we generalize the sequence processing paradigm to admit infinite sequences. More exercises, and I think we are done. I think we are done. Not yet. Nested mappings. Oh, cool. Picture language. I think I will stop here. I'll do a bunch of exercises and we will continue from nested mappings. So see you in the next video. Ciao ciao.